Okay, so right. So before answering that question, let me convince you that this is correct, at least in one case. So can you give me an example of one case? Well, this statement is obviously correct. Well, so to speak. Obviously.
Take a point and...
I just take a point, yeah. So if I take a point,
then it will just be connected components on one side and there will be rank on the other
side. Yes. So if X is a point, so if X is a point, then of course, homotopy class of points into Fred H is the set of path components of Fred. And we saw that this is just isomorphic to Z. And in fact, isomorphism is done by index, right? So that's one side. The other side, K0 of a point. So for, yeah, vector bundles over just isomorphism class of vector bundles, which are vector spaces, so that's Z. So that's a group completion of rank of the vector spaces that generate vector bundles over points. So this is, so in this case, obviously, the map is actually true. So at least in one case, we can directly check that. But anything beyond that, you have to go through this. But now let me draw one conclusion, I mean, immediate conclusion of this, which is useful, is this. So this is corollary of Atiyah-Jaenich. So let's take X equal to Sn, right? So then what we know is that the homotopy classes of maps from Sn into Fred, the statement says that this is isomorphic to K theory of Sn. Now, K theory of Sn, it's not easy to calculate, but it's done by Bott periodicity. So Bott periodicity. It says that K theory of Sn is equal to Z direct sum Z if n is even. Let me write it like this, n is even. And it's Z if n is odd. So basically, this Z always has to be there for K theory of the spaces, right? Because there is always this trivial vector bundle, which has, by rank, creates this copy of Z. And this basically K theory of, so it's a projection of your space into a point. It gives you an embedding of Z into your K group. So there's always a copy of Z no matter what for spaces, because you have this projection, you have this map from your space X into a point, right? So this is always there, but the non-trivial part is for n equal to even, which is there is only one extra component you have to add. This is the difficult part of Bott periodicity. Okay, so then we know that this result. So from here, we can conclude that actually, so, but what is pi n now? What is pi n of Fred H? So pi n of Fred H are the same thing, almost same thing as this. So maps from Sn to Fred, but they have to be based maps, right? They have to be based loops or based spheres, right? So let me put it like this. phi n of Fred H. Oh, I need it. Is actually equal to Sn, right? And Fred H, but based. You can go into different components, right? You generate this. So this corresponds to one copy here, this Z copy, trivial copy. And then just easily actually shows that this bot calculation shows that this is equal to now Z if n is even, and is 0 if n is odd. So this is the result. This is a very important result, right? Gives us something about homotopic groups of space of Fredholm operators. Of course, we are always talking about the connected component. I mean, the component that contains one, but other components are homotopy equivalent to this. So if you know it in this case, so that's it. So for n equal to even is Z, for n equal to odd is 0. So this is, you can keep this in mind. That's another important bit. For example, pi 1 is 0. Any loop of Fredholm operators based at 1 is contractible. I mean, that's not an easy, to me, it doesn't seem like an easy result. So,
sorry, what are the generators?
Sorry?
Can we describe the generators?
Generators of this, no, I can't right now describe it. But I think it's known. I think it's not, I think it's known. But right now, I don't know. Another thing is to describe cohomology of these things. That's another interesting problem, which I think it's been done, but I don't know right now offhand. I don't know. So these are kind of starting of some very interesting work on topology of Fredholm operators. That's okay. So I think we are done with basic stuff. You have any questions? Okay, so now, so what we did so far, we did abstract Fredholm operators, both algebraic and analytic level. We did examples, several examples, and we looked at some aspects of this Atiyah-Jaenich. But now, the proper kind of index theory did not start from these Toeplitz operators, really. It started from questions in geometric analysis, differential topology, and things like that. So let me, but again, let me put the question like this now, because now we know what Fredholm operators are. But now let me ask this question: where Fredholm operators come from? So that's a fair question, right? So we have this abstract theory to start with. We can write Fredholm operators of any index, fine. And we have a little bit of interesting analytic theory with Toeplitz operators. But the question is that all? Is that all that there is to these Fredholm operators we can get? Is there any geometric situation, for example, one can construct Fredholm operators, basically where they come from? So this question has an answer in some sense. The answer is that a large class of Fredholm operators actually Come from elliptic partial differential operators on compact manifolds. Come from, so elliptic PDEs on compact manifolds. So the emphasis here is on two things. First of all, elliptic, of course, PDEs, but then compact. And more specifically, they are obtained as a result of finiteness and regularity theorems for such elliptic PDEs. So this is finiteness and regularity theorem for such things guarantees that you have Fredholm operators. And once you understand this result, this is a very important insight from analysis, from geometric analysis, analysis on manifolds. So this is very, very important, valuable insight by itself, that if you have elliptic PDEs on compact manifolds, you do get, in very strong sense, you do get these Fredholm operators. Whether you want to compute this index or not, that's another issue, but by itself is a very important piece of analysis involved here. So our first task is to actually get the setting for these things, discuss these things, and prove this theorem somehow, at least give the main ideas in the proof. Okay? So the first thing we have to understand is what is an partial differential operator on manifolds. So the first thing to understand is partial differential operators. So this is what we call PDEs. Right? So the simplest case where you can discuss PDEs are PDEs that act on Rn, and that's fairly simple. First of all, on Rn, a PDE, partial differential on Rn, is an operator of this form, P equal to sigma AIX di. Okay, so say absolute value of I less than or equal to n. Equal to sigma AIX di. So what is this? I mean, so I'm using obviously a notation here. So I is a multi-index, I1, I2, In. Its total degree is I1 plus I2 plus In. And then you write di, you mean d dx1, sorry, d dx1, so say di1 dx1 I1, and then din dxn in. So what you do, you take a partial differentiation I1 with respect to x1 I1 times and up to In times, multiply them, you know these operators commute. Okay, so this is di, and this x, of course, is just, can you see this? Yes, x1, xn, and ai. Now, you can just say these are smooth functions. You can be more specific about them if you need it, if they are needed, but right now I just say they are smooth functions. So AI X is a shorthand for a I1, In, say X1, Xn. These are functions of n variables and belong to C infinity of Rn. And you can think of C infinity of Rn complex value. It doesn't matter. Coefficients in C. Take values in C. Okay? So that's what a PDE is, right? In very algebraic expression like that. Of course, these PDEs act on functions, right? P from C infinity of Rn, gain complex value, defines a map to itself, right? So because P of F can just take partial derivatives and then multiply by these AIs. So this is the way it acts, right? So some AIX at the I of F. Okay, so that's okay. So this is maybe I can denote it by differential operators DO on Rn. Now, one interesting thing about this DO, these differential operators, is that it's an algebra, actually. It's not just a set of objects, abstract objects. It's an algebra. You can multiply these things. It's an algebra. Now, to describe the algebra structure, I just appeal to your intuition. I don't give a formal definition because there is a formula that formally defines the product of these two things, P1, P2. But it's really, if you want, it's just composition of these operators. It's just composition operators. I mean, very kind of intuitive notion of operators here. We are using composition of operators. The main thing is to show that actually, if you compose two of these things, the result is going to be again of that form. So this, you know, this. So let me write it like this. For example, imagine you have A1. D1, you want to compose it with this operator. So these are both first order, for example, D2. So what is this guy? How does it act? Well, I mean, what you do, you just imagine you want to act it on some f, right? Some function f like that. So this is A1x, D1, then composed with acting on, rather, A2 of x, right, D2 of F. And then you have to act like this. So this is A1X, D1, A2X times D2F. Yes, and then plus A1X, and then A2X, D1, D2. So then the result of A1, D1 composed with A2, D2 comes out to be equal to A1, D1, A2, D2 plus A1, A2, D1, D2. So you can see that in general, you can write a formula. The formula is known. It's not very difficult to work it out, but I don't remember, but it doesn't matter for us right now. There's a product formula that you can write any two such things and then turn it into a differential operator again. So this is an algebra. Now, the important thing about this algebra is that it's not a commutative algebra, right? So note, not commutative. Well, I mean, DO of Rn is not commutative. So DO of Rn is not. That's what I mean. It's not commutative. Okay. But now, there is something though that you can always make sure that this is correct. Let me mention here the leading symbol. First of all, the symbol and then the leading symbol. So let me write a symbol of this differential operator P. So this is this expression. So it's going to be a function of two n variables. You basically replace these di's by minus I xci. So let me say what you do. So this is a symbol of P. I denote it by some xc, some symbol. The value of symbol of P at x and c is equal to sum ai of x. Now, I want to replace di not by xc though, but by minus id, minus ixc. Let me explain. So first of all, what is xc? Xc is equal to xc1 xn, okay? And then when I write xci, I mean xc1 i1 cn in. And when I say minus ixc, it just means minus ixc1 minus ixn, right? So if you think about it like this, the symbol is a function of two n variables, and it's very important to think of the second variable as belonging actually to the dual. I use the xc to the dual vector space. Right now it doesn't matter much, but soon it will matter. So, okay. Now this symbol, the way it is, it's useless for us. For some people, it's not. But what is really important for us is the principal symbol. So, principal symbol. So this I denote by sigma p x and c. So the principal symbol is you just take the top degree terms and you drop the rest. So that's sigma ai x. So I would say minus ixi. So absolute value of I is equal to n, the top degree, the top part. Right? So we just take the topmost part. Now, it's not difficult to see that actually when you multiply two differential operators, the symbol of the product has a complicated relation to the symbol of individual parts, but the top part is always very easy to understand. So let me write it like this. So it's a lemma, symbol of the, so now the principal symbol, so now I have to put this, so there is this P here, but these two P's are very different. This is a principal symbol maybe, sorry, but this P is the operator. So the principal symbol of P1, P2, XC is the product of the principal symbols. Is equal to sigma P, P1 xc sigma P2. And the proof is, of course, you have to know something about the product, right? I mean, the thing is P1, P2 is always of this form, sigma AI x D. AI x, and then, so we have to multiply the top parts. Then Bj x di dj, absolute value of I is equal to, we have to make sure that absolute value of I plus j is equal to degrees n1 plus n2. And so di dj, yes, plus lower order terms. Right. So you can check that. So n1 is degree of E1, n2 is degree of E2. So the degree, I did not formally define it, but you can sense what the definition is. Degree of this operator is the biggest multi-index, the total degree of the multi-index I, such that AI is non-zero, right? At least one of those AI's, maximum degree should be non-zero. So that's the degree, and then we just make sure that we are taking the top, the sum of the two things is maximum possible, which is n1 plus n2. Everything else has a lower order. And this is, so if you use this result from here, it follows that, of course, principal symbols multiply, right? Any questions or? So let me give one example actually of this symbol calculation and then move on. So imagine you have like flat Laplacian. So what is it? This is, of course, a differential operator. This is sum d2 dxi squared, right? So that's is a second order PDE, right? And what is its symbol? I mean, principal symbol. We have to replace ddx by ixc. So basically, this is going to be I2 is -1, so minus sum ci squared, right? I from 1 to n. This is the principal symbol of it. Now, if you had some extra term here, like plus some AI x di, for example, some first order terms, we wouldn't affect the principal symbol. The subleading terms wouldn't affect the principal symbol. Of course, it would change the symbol, but I will tell you in some sense, these lower order terms doesn't matter for us. The thing that matters, so life in this case is beautiful, is very good, it's helping us. That we just care about the leading symbol. Like, okay, so keep this in mind, minus sigma ci squared. But now, let me give another example. What is your second favorite differential operator? So your first favorite differential operator, of course, should be Laplacian, right? You have no choice. So what is your second favorite differential operator?
Delbar.
What's that?
Delbar.
Delbar. Okay, very good. So Delbar. This is del z bar. So 1/2 ddxi, I mean ddx, right? Plus I ddy. Perfect. That's Delbar. So now, what is the symbol of this guy? Principal symbol of Delbar. Xc is equal to 1/2 minus I C1. And then here I just multiply by I, just I times I is minus 1 minus C2. Okay? That's it. So this is like minus 1/2. I mean, okay, so why should I write it even better? That's good. I mean, I don't need. So Delbar is an important operator. We keep it in mind. What else? How about wave operator, wave equation, right? So another example would be wave operator. So this is box, and the simplest case is d2 dx2 in 1 plus 1 d. d2 dx2 minus d2 dy 2, right? The difference now here. So what is the symbol of this guy? Well, that's minus C1 squared plus C2 squared. See? We calculate the symbol like that, right? Minus C1 squared plus C2 squared. Okay, of course, if you have lower order terms, again, you can have similar thing. But right now, maybe it doesn't matter much. We should just look at this now. Okay, now comes important definition. An operator is called elliptic. An operator, I mean, a differential operator is called elliptic. So that's an amazing, very, very important definition. It's called elliptic if its principal symbol is different from 0 for all x and for all c different from 0. So that's the condition. So away from the 0 locus, which is, you see, this c is, I mean, this sigma p in c, I'm saying, is a homogeneous function of degree capital N, right? It's a homogeneous function of degree N in C. So we cannot expect this to be non-zero for all C because it's 0 at 0. But away from that, it should be different from 0. And that's the definition of ellipticity. Okay? So now let's look at these examples and check which, so we have 3 examples. Let's check in which of these 3 cases we have an elliptic operator. Obviously, Laplacian is elliptic, right? Because this is different from 0, away from 0, right? So let me then write it. So is elliptic. By this calculation we did here. The Delbar operator is also elliptic. If you are different from 0, 0, then at least one of these 2 things is 0 because I, it's very, very important. I is a complex number, does not mix with this real number. So as soon as one of them is non-zero, it's not C1 plus C2, it's I C1 plus C2. Okay. So this Delbar is elliptic, but this wave operator is not elliptic. So this is an important observation now that we should keep in mind. Okay, so basically for a lot of different things, differential operators will be able to say whether they are elliptic or not. Sometimes we have to work harder, but we should keep this in mind. But look at this wave operator. The symbol is 0 on the light cone, right? In the wave operator, symbol is 0 on the whole light cone. I mean, in this case, on the light cone. C1 squared minus C2 squared equal to 0. So this creates a lot of issues for analysis of wave operators, which puts it in completely opposite camp as elliptic operators. It's totally different world. And in some sense, these are much more complicated to understand than elliptic operators. So, any questions? Okay. So before we finish, I think we're almost done. If you allow me 5 minutes, I will. Now, of course, this is not enough. These are just scalar operators on Rn. We have to go to vector bundles over manifolds. But you see, the thing is now, so first of all, we go to vector valued functions. So differential operators. Acting on Rn and some Cn to itself, acting on vector valued functions on this. So on sections or smooth sections of a vector bundle, in this case, trivial vector bundle over R. So what are they? The expression is exactly as before. Right? Except that these guys are now matrix valued functions, right? So AI of X belong to Mn of smooth functions on R. They're just matrix valued functions. So once you have a column vector belonging here, you apply these partial differential operators component-wise, and then you multiply by this matrix, and then you get a column vector again. So that's the way it works. Right? And again, principal symbol is a matrix valued function. So this is, so here absolute value of I less than or equal to n. So that's sum AI of X minus I C I absolute value of I equal to n. So what is this guy? So this guy now, sigma p, principal symbol of X and C. For each X, for each C is an element of n by n matrices on C. So it's a matrix valued function of two variables, X and C. So you can think of this sigma p as a function going from Rn cross Rn star to n of C. And again, I can define a Fredholm operator in this case, an elliptic operator to be this, so definition. Same definition as before, P is called elliptic. If this principal symbol is different from 0, away from C equal to 0. If sigma p, I mean different from 0, I mean invertible, okay? So is invertible matrix for all X, for all C different functions. So this is now a good definition for us of elliptic operators. This should satisfy this condition. And finally, so we have worked on the vector valued functions. And of course, now then the next step is to go to vector bundles. But then it's clear what to do, right? For vector bundles, at least one aspect is clear. I mean, there is something to check. So then let E and F be smooth, complex vector bundles over a manifold, say M. Then a differential operator, partial differential operator, a PDE, E from C infinity of, so let me put it like this, C infinity of ME to C infinity of MF. So this is a space of smooth sections of this bundle, smooth sections, is a linear map, P as above. I mean, by linear, I mean just C linear. Right? Because these sections of vector bundles, at least they have a C linear structure, right? You can, if you have a section, you can multiply by C. So this makes sense. And you can add two sections, you get a section, right? So is a C linear map like that, P, such that now locally, if you fix frames and go to local frames, you get one of these things. So here I have to, I forgot to extend this from Rn, Cn to Rn and Cm, but okay, so let me write it like this now. It is a C linear map, P, such that in every local frames for E and F, the resulting operator so this resulting operator in these frames, I can write it like this. They go from, say, now there is something I still have to do, but let me just not worry too much about it. From C infinity of U and Cn to C infinity of U and Cn. Oh gosh, no, I don't need that. Where is this? Say n prime, where n is rank of E, n prime is rank of this F, and this U is a local open set in M open. And by this, I really mean space of a smooth functions, not on U itself, but on image of U under a local chart. So you know how to fix this, right? So it is a differential operator. So what do I mean is that if you go to local charts, you can always write your operator of this form, where this AI are n prime by n matrix valued functions, right? Is this definition clear? Make sure I understand this. It's not a difficult definition, but right now, so it's kind of important to understand it. So at this stage, so I mean, we can define these differential operators like this. I mean, partial differential operators. But now the thing is how we are going to define the symbol of such operators. So this.
So
Yeah.
question, So in this definition, so I can consider the Delbar operators as vector valued things. So I can look at a complex vector bundle and look at the Delbar operator for it, right?
Of course, yeah, sure.
For sections, so it acts on the space of sections of the complex vector bundle. So for under this definition, that Delbar operator is not elliptic, right? Because under change of transition maps, because it's not a holomorphic transition map, your condition will not be satisfied. Is that correct?
I'm not sure what you mean exactly, but let me write it down about Delbar. So in general now, so what is the context for Delbar operator? Okay, so the context for Delbar operators is, in general, if you have a complex manifold, right? So imagine you have a complex manifold. Okay. And in general, we have this Delbar operator. At least, I mean, you can take Delbar operators with coefficients in complex vector bundles also, but let's forget about that. Delbar operators, these are maps that go from omega PQ of M to omega, so P.
No, I wanted to take coefficients with values in complex vector bundles actually, because that's where my doubt is. So
No, that's okay. But I mean, this operator is not. I mean, is a differential operator. We'll check that.
Yeah. So this we checked. This is a elliptic PDE that I'm fine.
No, it's not elliptic PDE.
Oh, it's not.
No, I mean that's in one dimension we check. But here I'm very general. You see, I'm over M and I'm working with P and Q, right? So in general, this is not an elliptic.
Oh,
okay, because dimensions even don't match, right? So here, for example, let's look at this case. A consequence of ellipticity is that the rank of these vector bundles have to be the same. Well, I didn't define even ellipticity, so why do I jumping ahead of myself?
Oh, okay. Sorry.
Maybe I should. Yeah, maybe I should. Maybe we should wait a little bit and then we'll discuss ellipticity. Yeah, I didn't define ellipticity, by the way, yet. So okay, so this is a PDE. I mean, this is, if you want, this is an example of a PDE, but we don't need it right now. So let me just. Okay, so this is an example of PDE. That's good. So this is Delbar operator. So what?
Sorry, okay. In the definition of PDE, I had a question in the definition of PDE. Then.
Okay, what is your definition? Your question? Yes.
Okay, now so suppose I look at Delbar with which takes values in a vector bundle, in a complex vector bundle, not holomorphic. Okay. So then I will tensor with the vector bundle E on both sides. Mm-hmm. That's that you have.
Yes.
So now so basically your definition says that under every trivialization, I should be getting the same expression, but.
No, not the same expression. You don't get the same expression. You get a differential operator. That's what I'm saying. You do get a differential operator. I'm not saying you get the same expression. If you change coordinates, the expressions will drastically change, even as
no, but they will be related by the transition map. They will transfer tensorially, is what you're saying.
Yes.
But suppose I took just a complex vector bundle, right?
Okay.
So then my transition maps are not holomorphic, they're just complex.
It doesn't matter. The issue is not holomorphicity at all here. The issue is just being a partial differential operator. That's a smooth story completely. It doesn't matter if it is holomorphic or not. It doesn't matter. We just worried about the smooth structure and being a PDE.
No. So my question basically stems from, suppose I looked at a set of solutions such that Delbar F is equal to 0, right?
That's a different issue. Yeah, you get holomorphic.
Exactly, and that is invariant. Sorry, that changes when I change the coordinates, because the change of coordinate maps is not holomorphic. So the set of solutions changes. So that is where my issue is.
No, the set of solutions won't change unless, well, I mean, if you take the same, so we will discuss it. So let me go back to
okay.
Because they have to develop enough language here so that these issues will be immediately resolved. I mean, these are very, very simple issues. We will resolve them immediately once we have some language in place. So what I was going to say in this case is that, so now I think it's very important to worry about the symbol now. This is a very, very important question, okay? So what is a principal symbol? Of a PDE, I mean, in partial differential operator, say P, going from C infinity of, my notation was ME, right? To C infinity of MF. Sorry, ME to MF. So this is now a very important question. We have to address this question. So what is the symbol? Okay, I mean the symbol. I mean principal symbol, right? So what you can do in this case, and people notice, is that the principal symbol sigma p, again principal, not x and c, is really defined for any x on M on your manifold M. And for any C on the cotangent bundle at X, okay? And is a map from the fiber over X of E to fiber over, oh my God, it's a storm, to fiber over X of F. So this is the thing. Okay, so now this is what you have to think about and do a calculation. So, okay, so the symbol, the principal symbol, not the symbol, the principal symbol of this operator P. Well, it's unfortunate that I'm using the same notation for P and for principal. They both start with P, but we understand. This is for principal, this is for the operator notation. The principal symbol of my operator is for any x on M and for any c on T star is defined as so what you have to do, you have to go into local coordinates and write your operator in this local coordinate. And frames. You have to fix both local coordinate and frame, right? By writing first your operator P, you can write it as sum AIX DI, right? Absolute value of I equals to N plus lower order terms. And then what you do, then you just replace this DI by these cotangent variables. So we just say this now, once you have this dual values, this now is something that's going from EX, which is isomorphic to Cn to Fx which is isomorphic under using these local frames. At each point, this gets isomorphic to maybe Cn prime. So, oh yeah, that's very unfortunate because I'm using n and n prime here. So this is a different one. So maybe rank P or rank Q would be in order. So okay, so this is P. Okay, this is the same. So technically, then what is principal symbol? So I can say principal symbol is a section of a bundle. So it's a kind of more highbrow definition is this. More so highbrow definition is that principal symbol belongs to smooth sections of X and pi star of, and so here is endomorphisms of pi star of E and pi star of F. So where pi from E to X, from F to X are these bundle maps. So maybe I have to fix this a bit. So for now, it doesn't matter just to give this exact highbrow definition. But just before I finish in 50 seconds, now there is a deep thing here to be proved. There's an important thing to be done here. You have to check that this definition is independent of choice of coordinates. That's very important. So this is a proposition. You have to do, I highly recommend you do it. That's an important part of the calculus here. Even in, do it in 1 or 2 dimensions. So proposition, definition of sigma p, principal symbol, is independent of the choice of coordinates and frames. That's very important. You should also try to understand why we are using the dual variable here. We are not using TM, tangent variable. We are using cotangent variable. That's an important part of covariance issues here, which is it's a very, very deep thing. This is related to ideas of classical mechanics and quantization and relation to quantum mechanics and all this. So we have to use this momentum variable, the conjugate variable in the dual direction. In order, you can choose like C to be in TM if you want, but then you notice that this proposition won't be true. So you haven't defined something invariant. These are things to be checked. So this is kind of messy, but at least you do it in 1 or 2 dimensions. And in that case, then you see what's going on. Okay, so then next time, what we'll do is to start looking at these elliptic PDEs, and then start proving this regularity and finiteness theorem. So why is elliptic PDEs define Fredholm operator, and in what sense they are Fredholm operator? That's the first step here. Once we take that analysis out of the way, then we can just think about the index of that Fredholm operator and why we can calculate the index. So that's the path that eventually leads to Atiyah-Singer index theorem. So okay, so that's it. If you have any questions, please ask. I will give you some references. That's important to have some references. So maybe even I can post the references on the YouTube channel sometimes. So. Okay, so guys, thank you very much. Thank you all. So if you don't think there's no questions, and the rain still is going on, so maybe you want to enjoy the rest of the day in the rain. So, okay, guys, have a good day. Take care.